Thank you very much. Thanks for inviting me. And well, it's a great pleasure to be here with Yuri and everybody else. So my mathematical genealogy looked kind of nice and clean until I learned that it's not all as it looks. And I have some unaccounted relative, well, scientifically speaking. So it turns out there was a person who spent a couple of years at UL State University and managed to supervise my PhD supervisor for a while, not completely. Then he left. And somehow it turns out that he lives in like 2 hours drive from us in Seattle. That was Yuri, of course. And actually I learned it pretty late. So it was a very pleasant surprise. Thank you for being at Microsoft Research for so long. next to Simon Fraser, basically. And on the technical side, he also taught me how to type formulas in PowerPoint. So that was very useful. Well, anyway, that's what the topic I'm going to talk about. That's a joint work with Standard Zivny from the University of Oxford. So I start with the something. No, I'm not allowed to do that, apparently. Okay. No. Okay. So some button should work. With a simple system of linear equations. So 9 variables, well, equations go like row-wise and column-wise, obviously. And well, if you look at them, it's kind of obvious that it's inconsistent, right? Because if we say add up all the variables row-wise, we of course get 0. If we add up variables column-wise, we of course get 1, right? So we cannot satisfy that. But again, it's not all as it looks. And if we allow ourselves a little bit more than just this addition with integers and or zeros and twos, zeros and ones, well, we may get something. So first of all, I want to rewrite it in the multiplicative form, right? So plus is replaced with multiplication, 0 with ones, and 1 with -1. Well, nothing changed. It's still inconsistent, no problem. But what if instead of numbers, we assign values as matrices, for instance? Does it help? It turns out it does. Well, if we start with famous matrices, well, they are very well known in quantum mechanics, for instance. Well, these are Pauli matrices, of course. Then this is a solution to this system of equations. Okay, I probably should wait a couple of minutes till you check that this is indeed a solution. Well, I promise it is. Well, this is Kronecker product, of course, right? This is Kronecker product, of course. Yes, tensor product, that's right. So what is going on here? Well, obviously the catch here is that while addition or multiplication of numbers is commutative, and so it doesn't matter which way we multiply, this way or this way, matrices or operators, linear operators, are not commutative, right? And therefore it may change the result if we multiply them this way or that way. So that kind of explains the title commutative versus non-commutative stuff. And well, I will talk about that a little bit later. So this is a so-called magic square, because people in quantum mechanics were so impressed when it was invented by Mermin. It actually, one of the consequences of that is a very short proof of this, that quantum mechanics cannot be explained with hidden variables and stuff like this. Right, so it plays a really important role. So from the quantum point of view, what we have here is something like this. Well, every equation is some sort of an observable, whatever we can observe over a system, right? So here we have 6 observables. And of course, if we can observe something like measure, for instance, then we have kind of more restrictions on what kind of values we may have and all and everything like that. So for instance, since when we measure something in quantum mechanics, we have to get something classical, right? Zeros and ones, basically, not some kind of weird operators. This means that the solutions here have to be related to each other somehow. And well, what they should be in this case is that they should be pairwise commutative and normal. In this case, well, they can be diagonalized simultaneously. And basically, you can think for each of the equations that those things are just some kind of superpositions of classical solution. So that's basically the idea here. So we have this complicated system. We can observe it this way or that way. When we observe it, everything is fine. But what happens behind the scenes is kind of more complicated than that. Right? So that's the overall idea. Okay. Now there is one more word from the title that I need to explain, of course. And the idea here is that okay, well, we have these linear equations, etc., etc. What else can we do? Again, quantum people invented more constructions like that. So this is magic square. They also invented a pentagram, which is probably, that one should be called magic in a way, but anyway. So what if we try to kind of generalize that? Instead of just systems of linear equations, maybe something more, okay? And we are going to generalize it, well, quite a bit. So we are going to look at constraint satisfaction problem, the CSP. Well, I give a brief definition. It's fairly simple. So we have a bunch of variables, like in that linear system. We have a set of values, like 0, 1 in that system. And we also have a set of constraints. We may think about them as predicates on the domain. Right, so what we want to find out if we can satisfy all the constraints simultaneously, meaning that we need to find an assignment that satisfies every constraint. Okay, so a system of linear equations is one example of a CSP. Well, in the majority of cases, we don't want to allow just everything, and we would normally say, okay, well, those predicates cannot be just anything. They should be linear equations, for instance, or something like this. So we would restrict the choice of possible predicates. In this case, we will say, okay, we have this set of allowed predicates. We call it constraint language. And our CSP is only allowed to use these predicates and nothing else. So for instance, what we've seen from linear equations is this. Just every constraint is a linear equation, and that would be a CSP over Fi in predicates. Well, I will denote it by gamma Fi, which involves all possible predicates like this. So that is expressible by a linear equation. Well, that's a good question, because I'm not sure why there is a 1.5 here, but yeah, well, just imagine it's some number set. Doesn't matter. It's just anything goes. See? Okay, magic. Right. So a minor problem here is, of course, okay, so we have that. Now what we want to follow the magic square, right? And somehow we would like to be able to use those operators here. Okay, if it's equations, well, maybe, right? We can convert it to multiplication and blah, blah, blah. But what if it's not linear equations? What if it's something more complicated? How, in general, we can satisfy or try to assign values to a CSP that are operators in some Hilbert space? Well, we can do that using a simple trick that we actually used with that magic square, also in a sort of very rudimentary way. So let's try to do it in a more general way. How do we represent any predicate as something kind of less concrete? So what we are going to do? Suppose we have a constraint language, gamma. So it's a bunch of predicates relations over some finite set. Well, it doesn't matter which set it is. So I will assume that this is actually a set of complex numbers. Why not? After all, right? Clearly, if I have, say, 5 element sets, I can choose 5 complex numbers and just use those numbers instead of my elements. But of course, I will be a lot more careful. Okay? So I take an instance. Suppose I have those variables and so on. So what I'm going to do now, I take a constraint. So that's my predicate. These are the variables the predicate is imposed onto. So what I'm going to do, I'm going to find a complex polynomial, right, such whose zeros are exactly the tuples from here. If the base set, if the domain is finite, right, this is a finite set, I can always do that. I may get a polynomial of pretty high degree, but I don't care. There is a polynomial like this. I can interpolate such a predicate. So now instead of just a bunch of tuples or a predicate, I have a polynomial. And of course, if I have a polynomial, I can use whatever I want, operators, matrices, or anything like this. So that's the conversion into something that I can, where I can use those matrices, operators, etc. Okay? So what would be a solution, a solution to such a CSP? Again, similar to magic square. Well, we cannot take just any matrices operators because remember those observables, they have to commute, etc., etc. So the requirements will be like that. Well, first of all, I will assume that the complex numbers I choose, not just any complex numbers, I will choose them more carefully, and that's just roots of unity. Well, they are convenient, I can multiply them nicely and all this stuff, right? Okay. So suppose, well, now I want to find an assignment, a solution. So I take my instance, again, I have this set of variables, I fix a Hilbert space. It can be finite dimensional, but actually it can also be infinite dimensional. So these things work in infinite dimensional spaces as well, right? So we have a huge choice of what we can do here. Okay, so I say that a bunch of operators on H is an operator solution if several conditions hold. Well, first of all, every operator is normal, and it's kind of finite order or order D. So if I raise it to the power of D, I get the identity operator. Okay. Well, clearly, if I want infinite dimensional, I will have to say that, well, it's not just kind of equal. It has to be like that almost everywhere and stuff like that, but it doesn't matter. Okay. For every constraint, the operators involved in this constraint must commute. And what I get from that is by the spectral theorem, this means that if I take operators from the same constraint, I can simultaneously diagonalize them. Right? I cannot diagonalize all of those, but for each constraint, I can diagonalize them. They're not linear. It's a linear operator. Matrix. Linear operator. Yes. Linear operator. Well, and finally, if I plug them into the corresponding polynomial, of course, I need to get 0. I need to get a 0. So then I would say, well, this is a solution. Well, it's pretty much the same transformation as we did with magic square. You can check that if you take tensor products of those poly matrices, everything is satisfied and all this stuff. Okay. So what would I like to know? Well, clearly, as we saw in magic square, right, it doesn't have a classic solution, but it has this operator solution. And that's the intriguing property. Clearly, if my CSP has a classic solution, it also has operator solution. Well, I can take diagonal matrices, no problem, right? And multiply them the same way as I would just combine those finite values. But what if it doesn't have a classic solution, but can it have an operator one? Okay, so that's the research question is to figure out when my CSP has the satisfiability gap, meaning that it doesn't have well, there is an instance for which there is no classic solution, but there is an operator one, like magic square, for instance. Okay, so that's what I will try to answer. This is what I will try to answer. By the way, well, we can go a little bit deeper. For instance, we can ask, well, for which dimensions of Hilbert space we can have this gap? Finite versus infinite dimension. Well, dimension 3 versus dimension 5, etc., etc. Well, I will kind of ignore that except for this finite infinite. but overall, well, that's also a possibility. Okay. In the very simple case, Albert Facchion and what's his name? No, Severini. That's the quantum person here. Anyway, so they basically did that in the case when D equals 2 for 2-element sets, for 2-element domains. Right? Well, and we're kind of more ambitious. We want to generalize that. Okay. So let's see. It turns out, if you look at a result by Albert Facchion and the third guy, right? Well, they didn't say that for some reason, but you can kind of see where the borderline is roughly, right? And this is about a completely unrelated property of CSPs, which is called bounded width. And then if you kind of look at everything around this bounded width stuff, it's really amazing that it works like that. So anyway, what is bounded width? I don't want to give a sort of precise definitions, of course, but roughly speaking, we say that CSP has bounded width if it can be solved by local propagation algorithms, meaning that every time we look at only few variables at a time. So for instance, for linear equations, you cannot do that, right? Gaussian elimination needs to look at all variables at the same time. So it doesn't work locally. Well, Gaussian elimination is a global algorithm, not one like this. And equivalently, a CSP like this, a bounded width, is exactly those that are solved by a data log program. So a simple example of a data log program, I claim it solves the two-coloring problem, bipartiteness, right? So that's the predicate, the H relation of my graph. This is an IDB, well, some kind of auxiliary relation. And basically it says the following. Well, we assign, to that auxiliary one, we initialize it with that relation, with the edge relation, and we can also add those tuples that satisfy this. Right, here you have like exists, Z and T, and also and, right? So what kind of pairs will we have here? Well, clearly those that are connected with a path of odd length. Length 1, if this two length 1, then that would be length 3, and so on and so forth. And then in the end, we ask, is it true that there is an X that satisfies this? So basically we ask, is there a cycle of odd length? So in that sense, two-coloring is solvable. Well, it gives the right answer. It's non-bipartite, for instance, so not two-colorable, right? By using this data log program. Well, if we kind of use more complicated ones, then we can solve all CSPs of bounded width using data log, and that's another characterization of the class. So local propagation, data log programs, well, obviously some fixed point logic is hidden here, and so on and so forth. It's a really, really interesting class. Really interesting. And now it's also somehow related to this quantum operator side of the CSP. Okay. Again, there are many local propagation algorithms. The one that we are going to use is a very kind of simplified one. So for instance, if we look at this data log program for two-colorability, right, it's quadratic, and Yuri told us that quadratic isn't good, right? So we want something really simple, right? Better linear one. So another algorithm that solves all CSPs of bounded width, which is linear R consistency. Also linear is not because it works for linear time, but anyway. So it works as follows. I have a CSP instance. Again, I kind of set up domains for each variables separately, and I will iterate this thing until everything stabilizes. So if I look at two variables, and if so happened, then in some constraint, where both of them appear, right? A cannot be assigned to xj, right? Given the restrictions on xl. So every time we just look at a variable, at a constraint, and check if we still can sort of assign some value to that variable. If we cannot, well, remove that variable from the domain and keep going. Okay? So this is a linear consistency. It doesn't solve all CSPs of bounded width, but a minor generalization does. So, and again, that's a kind of weird trick that somehow makes all these algorithms much more powerful. So the trick is this. Again, I start with a CSP instance. I would run linear consistency, no problem. And then I run the actual algorithm. I would do the following. I take a variable, I fix a value for that variable, run this linear consistency. If I get some contradiction, I say, okay, this variable cannot be assigned that value, remove the value. Okay? So that is called singleton linear consistency. And this one solves all CSPs of bounded. But it is much, much faster than something else. So we are going to use this one. Okay? All right. So what can we do in terms of operator solutions and this bounded width? Okay. If our CSP has bounded width, there is no satisfiability gap. Well, why is that? And how can we prove this? So if you think about it, well, the most natural way of proving something like this is this. Well, suppose I take a CSP of bounded width. Suppose it doesn't have a classic solution. What does it mean? This means that if I run one of those propagation algorithms like Slack, it will find a contradiction. I will kind of substitute this value, run this R consistency, et cetera, and at some point it will say, okay, sorry, but you cannot assign this variable anything. So no solution. This is what would happen. Okay? The good thing here is that remember that we can encode constraints with polynomials. So basically, if we run that propagation algorithm, it corresponds more or less to some kind of polynomial calculus. Right? If we assign this value, combine a couple of polynomials, well, we get some other polynomial, and in the end, we get that one has to be equal to 0. If we can do that at the level of polynomials, of course, no operator solution can exist because it still has to satisfy polynomials. And if polynomials are not satisfiable at all, like 1 equals 0, of course, well, we cannot satisfy it with operators as well. So the no gap side is basically proved by some sort of polynomial calculus. Okay? The interesting part is how to prove that when there is a gap. Okay? That's kind of a little bit more involved and interesting side. Okay? So first of all, as we saw, the standard example of a CSP with satisfiability gap is that system of linear equations. Okay. So what we would like to do, we would start with our constraint language gamma and find those systems of linear equations there somehow. So the main question is how. What is this mechanism that would allow us to not only find those systems of linear equations, but find them in some kind of meaningful way? Okay, well, for that, we don't need to think too much because in CSP, or at least the algebraic side of the CSP, things are very well known. And what we need to do is to use primitive positive definition. This will give us everything. So we say that a relation is primitive positive definable in gamma if we can express it like this. So the relation, well, that's a primitive positive formula. There are some variables. Q1, Qn are from gamma, and those are just some selection of variables from x and y. Some selection of variables from x and y. Okay? Okay, so what is good about that if we have a language, gamma, we can define some other language, say delta, and if CSP of delta has a gap, then CSP of gamma has a gap. So now the direction is kind of clear. We need to start here. We need to define some linear equations. Linear equations have a gap. Therefore, this one will have a gap. Okay? That's the strategy anyway. But it's a little bit tricky, unfortunately. So I will kind of list the main ideas. How much time do you have? 5 minutes?
10 minutes.
10 minutes. Okay.
Well,
Okay. So one good thing is that we know very well when our CSP does not have bounded width. Well, and also when it does have a bounded width. Well, it should be not, right? Does not have bounded width. It happens if and only if when there is a unary predicate, a set that is PP-definable in gamma, an equivalence relation on B, PP-definable in gamma, and the bunch of relations on B, again, PP-definable in gamma, such that if I take those relations, take the factor of them modulo theta, right? So I replace every element with its theta class. Then I get exactly this affine relations. So if I can do that, then does not have bounded width. Okay. So this is what we need to do. Somehow we need to take to kind of drag this satisfiability gap through all these hoops, right? Finding a predicate, well, finding the set, finding this and that, and so on and so forth. So that's a little bit tricky, as we shall see. But anyway, so what we can do by doing that? Well, we can almost prove what we want. The main result goes as follows. Well, first of all, if it has bounded width, it doesn't have satisfiability gap. Fantastic. Second, if we can express the way I showed in the previous slide, linear equations over Z2, then the magic square shows that CSP of gamma has satisfiability gap. So what about Z3? The interesting thing is that quantum people don't know. So there is no analog of magic square modulo 3. There is modulo 2, there is pentagram, but there is nothing modulo 3, or 5, or 4. Okay, there might be something 4. But anyway, so because it's divisible by 2. But anyway, if we switch to infinite dimensional classes, everything is nice again. Well, even for Z2, Z3, etc., we can find some analog of magic square, although it's pretty complicated. It's not yet published result by Slovsky. Okay, so this is the thing that is missing here. If someone finds a magic square modulo 3, what's going on? It wants to find a magic square modulo 3, obviously, right? So then it will be a complete classification, right? But not yet. Okay. So hope it will not die just yet. Okay. So what is the plan? The plan is, of course, well, if CSP doesn't have bounded width, find the right set, find the right equivalence relation, somehow simulate linear equations, well, get this language delta, and here we go. But in fact, it's a little bit tricky, because remember what we need to do. We start with those, right, where we have our solutions have, say, the domain of gamma has size d. So all our solutions, like normal operators, have order d. This guy here is smaller. It has order e. So now for this, I would have solutions that are normal operators of order e. And I want somehow to translate them into normal operators of completely different order. Right? That still commute where they need to commute. They still satisfy constraints where they need to satisfy constraints, and so on and so on. So that is a little bit tricky, right? And that's roughly what we need to overcome. So I have, I believe, a couple of slides roughly showing what we can do in this case. Okay, so let's do at least one of them. So for instance, how would I translate to smaller set? How would I translate all the solutions to smaller set? Suppose that I have a subset of roots of unity of order D. And that is base set of gamma. Or in general, it's smaller than D, so it's small. And this means that it's not good to use roots of unity of order D for that. Because remember, well, the order of those roots of unity must be exactly the size of the set. And in this case, they are not. So what do we do? Well, we take roots of unity of order E, obviously. We find a bijection between these two sets. Of course, this bijection can be interpolated by a polynomial. Everything is polynomial as long as things are finite. Okay? So we interpolate it as a polynomial, and we are going to use those polynomials for our translation. So for instance, if we have an operator solution for this guy, right? We apply our polynomial, we get new operators, and I would claim that this would be a solution for CSP of gamma. And that would be a solution for CSP of gamma. So again, since we work with polynomials, all transformations and so on has to be done through polynomials, and that's basically something like this. Again, well, I have some computation here. We need to check that all of those have the right order. Well, they do, because they're diagonalizable. We use this all the time, right? Again, well, we need to show that they're normal. Again, well, they're diagonalizable, et cetera, et cetera, et cetera. So we can check all these nice properties and conclude that, yes, indeed, we can do that. Okay, so that's roughly the ideas of operator non-commutative CSPs, and hope it's a little closer to the recent interest of Yuri about quantum computing. So that was my choice. Okay, thank you very much.